All right, here we go with number 4. Number 4, which is the young hockey player stands at rest on the ice. Right? Did I broadcast? I forgot to. Alright. Here we go. So, this is one that you, folks, this is one where you need the before, during, and after, right? Technically, if we had to rank this as a type of collision, what would we rank it as? Explosion. One object becomes multiple objects, right? So technically it's an explosion, but we know that even though it's an explosion, that momentum is conserved. So that's what I would write up here. Momentum is conserved in the explosion.
Momentum is conserved. Where's the dad? Where's Paul teacher? Is this a joke?
I've been asked by one of my AP class for jokes. None. 2 jokes, 1 class. You guys are my favorites.
He said, when does joke become a dad joke? When the punchline becomes a parent.
So remember, the before shows the momentum before anything happens. The after shows it afterwards. And the during shows the impulses that happen during the collision. So, my before is done. Right? Because how much momentum is there while the hockey player is standing there just with the helmet? None, so I don't have to draw any momentum vectors. There's no impulses before, there's impulses during. So the impulse, this is the impulse on the helmet, is in that direction. The impulse on the player is in that direction. Then, afterwards, the momentum of the helmet is that way, and the momentum of the player is that way. Yay! Alright, so let's see, what do they want to know? They want to know what is the mass of the hockey player? Okay. So we know that the momentum before has to equal the momentum after. Right? What's the momentum before? 0. Then the momentum after is made up of the momentum, these are vectors by the way, the momentum of the player and the momentum of the helmet. But what do we know about those two? They're in opposite directions. We need to make one negative, right? But the player negative? So notice I dropped my vector symbols because now I've shown that by the positive and negative. So the momentum of the player.
Can you draw a vector just does?
Well, no, you shouldn't. It's kind of like double negative. If you label as negative with the vector on it, it means in the opposite direction of the vector. So it's like a double negative. So, mass of the player, velocity of the player, or speed, because we are taking it in direction. Mass of the helmet, velocity or speed of the helmet. Oh, I think I know most of those, don't I? Let's see what I know. What I know. I don't know the mass of the player, but I know the mass of the helmet, speed of the helmet and the recoil speed. So, recoil speed for me was 0.2, I think, meters per second. Yep. Mass of my helmet was 1.2 kilograms and 6.0 meters per second. Yay! Well done. Recording would be good. So 7. We got the canoeist stand in the middle of her canoe.
Completely baffled. No idea what it was.
Yes, I believe so.
Well, this one is the same, actually the same idea as the one we just did. In that, what's the momentum of the system beforehand? Before she starts moving?
0.
0. So what must the momentum be?
Not 0.
It must stay at 0.
0.
So remember when I had the carts on the tracks and I exploded them?
Yeah.
And the center of mass stayed right above the support? That's what's going on here. Except rather than 2 carts moving out, she's moving one way and the canoe's moving the other way. To keep that momentum constant.
Yeah.
Just like if you stood on something really slippery. Like if you're, I don't know, on
Nice rink.
well, I'm trying to think if you were standing like on a boogie board on an ice rink, and you went to walk forward on it, it would move the other direction to try to maintain that 0 momentum.
Okay.
Okay, so that's what's happening. And if you've ever been in, a light boat / canoe pack and you've moved from one end to the other, you know it moves
Right.
the opposite direction.
That makes a lot of sense. Because you have to, because to move, you have to use friction.
Yeah, you have to push.
You apply an impulse to it, so
So
it moves and it applies the equal and opposite impulse to you.
It's impossible to really go anywhere there, right? Would you
Right.
Sit, oh, let me so
Wait, so
frustrated.
did this
Oh,
mean you put
Your
your paddles
wait,
the
so you
same
don't
speed
you
you
go?
go?
No. No, same force. Well, think about also how can you constantly move like that? What if you're on a big wheel?
I know.
Yeah.
I was thinking that.
Oh.
Standing in the middle of it, right at the beginning? Yes.
Yeah. So your diagrams. I'm gonna cheap out. There's my canoe.
Yeah.
It's kind of a clunky canoe. Yeah.
Wait, so the person on it, not.
Oh, that dude doesn't come out ahead.
Yeah, it's actually, you know, probably.
No, they said her canoe.
Yeah. But what's happening here? Are those hairs?
Yeah, I gave her some hair.
Did she gain hair after?
Yep.
That's the real question.
No, there was hair before.
There's hair before, right? Did she turn her head or something?
Her.
A lot of hair. Yeah, but this has got a circle. Well, act.
Yeah, the sun went down. Now it's dark.
I see.
I've been walking on that canoe for a while.
Yeah, it's pretty dangerous. Could fall in the lake.
I mean, you probably should walk on the canoe even if it's not dark.
You're fine.
What fun is that? Seriously. Just to make Brett happy. How's that, Brett?
I don't know how Brett feels about it. I think
Beautiful. And then I could write words like the momentum is conserved in the system. Be really also good to express, does the center of mass of the system move?
Oh, it does?
Not move, right. Because it has no momentum. Oh, come on. Later. So before equals momentum after. Everyone okay with me skipping all the steps in between and going momentum of the canoe equals the momentum of her. Mass of the canoe, speed of the canoe, mass of her, speed of her. Now, one thing to be careful of in those steps, you look at this and you know that it's momentum has velocity. But be careful, you've already taken care of that with all of the work beforehand, right? That one was negative, one was positive. So these really are the speeds you're putting in here. And then I think you know all that, right?
I just made another picture.
Yeah?
I turned like 350 feet to the ocean and getting ready. He's like, what? No, there'd be a bell.
Or did you just do like
No, the multiple choice you have to get right to get points. I think you lose some credit each time you get it wrong. But I think you can try more than once. All right. Number 9. Collision between the hammer and a rock lying loose on the ground can be considered approximately elastic. So right away, kinetic energy is conserved. That's one of the thoughts I should have in my head. So I'm going to write that right away. Is conserved. And of course, mom is conserved also. And so, and one reason I know that I have to take that into account is they don't give me actually, if without kinetic energy being conserved, there's not enough information to solve the problem. No.
So what do we put?
So we're going to use those two facts. Now I'm going to skip doing my diagrams because I think you guys get the idea of them, and I'm worried about time. So I'm going to start off with momentum before equals momentum after, and then down here I'll get to the kinetic energy before equals kinetic energy after. I'm going to end up with 2 different equations because there's, well, kinetic energy is a scalar.
Oh yeah.
So, yeah, magnitude is the only thing it has. That was good. So, momentum of the rock plus momentum of the hammer equals the momentum of the rock final plus the momentum of the hammer final. The momentum of the rock before it was hit is 0 because it was lying on the ground. The hammer is going to be the mass of the hammer, velocity of the hammer beforehand, and then mass of the rock, velocity of the rock final, plus mass of the hammer, velocity of the hammer final. Down here, kinetic energy of the rock plus kinetic energy of the hammer equals kinetic energy the rock final plus kinetic energy of the hammer final. Now, the rock is 0.2 kilograms, the hammer is 0.55 kilograms. So my thought is that after this collision, they're both going to be moving in the same direction, but not together. If like they had the exact same mass, I'd expect the hitter to stop and the hittee to move. If the hitter was lighter, they'd bounce backwards and the hittee would move forward. hit E and hit R. But since the hitter is heavier, it's going to move, keep moving in the same direction. Yeah. But it got dropped from the beginning part because it's 0. And we're gonna expand on that. Here again, this kinetic energy is 0, just like this one is 0 because it's not moving. So I've got 1/2 mass of the hammer, velocity of the hammer squared equals 1/2 mass of the rock, velocity of the rock final squared plus 1/2 mass of the hammer, velocity of the hammer final squared. Things that I know. Mass of the hammer, mass of the rock. The halves I can get rid of, right? I know the velocity of the hammer beforehand. So I don't know the velocity of the rock afterwards, the final velocity of it, or the final velocity of the hammer. But I have the same two variables in two equations. So can I solve it? Yeah. How should I solve it? Well, if you're upstairs, you should go through all the algebraic steps. Since you're down here on the fun first floor, use Wolfram Alpha.
On pH.
Fun with the pH. We'll put both equations in, separate by a comma, and say solve, and it will solve it.
How we can get rid of all 3 halves?
Because there's one in every term. Right?
Yeah.
So now you would just put in all, you want to put in all your values and then put it into Wolfram Alpha. Write out another step that has all your values in it. All right? But you can't reduce these any further than they are here and here, except by putting putting the values you know into it.
So Wolfram Alpha?
That's what I would use, one of the solvers. Wolfram will probably do this one the best. That's at the bottom of this page, this really useful page called Physics is Fun about Education. Down at the bottom of it, there are these mathematical solvers to save you from doing algebra. So, weight is an inelastic collision. I'm assuming part A wasn't that difficult for most people, right? It's all using the kinetic energy formula, right? But part B kind of stumped you because we know that in an inelastic collision, kinetic energy is not conserved. So, but we know that momentum is. So you've got to approach it through momentum, saying, okay, the momentum of the glider before equals the momentum of the two gliders together afterwards. Find its velocity from that, and then you can find its momentum, its kinetic energy. So I'm going to move to here. This is so this is number 8. So for part A, I'm just kinetic energy is 1/2 mv squared. Be careful. No, they give it nicely. They give it to you in kilograms and meters per second. For part B, you're going to have to use the momentum before equals momentum after. So you've got momentum of the part. How do they tell them apart? Oh, they're identical. So let's call them 1 and 2. Momentum of 1 equals the momentum of 1 and 2 together. So whatever the mass is times the velocity, the mass is going to double, and then you'll have a new velocity. And then, so here you're solving for the final velocity, and then use that in your kinetic energy. But it's, oops. It is
What do you mean? Use that.
2m and v final squared. So, using the momentum to find that velocity, then using that velocity to find the new kinetic energy. Does that make sense? Okay, the velocity is going to be half as much.
Question for the exit question.